So far, we have used a table to represent the decision-making process. But can we also use a graph to represent the decision-making process and find the optimal decision? The answer is yes. Indeed, we can use a graph like a tree we call decision tree to find the optimal decision. In the decision tree, we have round nodes, square nodes, branches. For example, in this decision tree, we use this square root to denote the decision node. We have some branches, we call decision branches. And then we have some round nodes. We use that to state the state node. We can also have some state branches. For example, in this case, starting from the decision node, we have 4 decision branches. That would be purchase A, purchase B, A and B, or do nothing. After each decision, we have 2 states of nature. For example, in this round 1, we have decision A for states of nature A and states of the nature B. In the end of the tree, we have the payoffs values. For example, if we use decision A and the state of nature is A as well, we get a payoff of 13. If the state of the nature is B, we have a value of -12. We can list all the payoffs values in the end of the branches, like -8 for decision B, for state of nature A, and so on. If we have the probability information, for example, 0.4 for state of nature A and 0.6 for state of nature B, we mark all those probability information on the branches of the state of nature. And now we can compute the game backward. For example, for decision A, we know we have state of nature A and B, and we have payoff for state of nature A, 13, and -12 for state of nature B. So we use 13 times 0.4 plus -12 times 0.6. We get -2 for the expected monetary value of decision A. Similarly, we use -A times 0.4 plus 11 times 0.6. We get expected monetary value of 3.4 for decision B. And we can get EMV equal to 1.4 for decision A and B and 0 for doing nothing. And actually, these 4 values are exactly the same as those values we get in the EMV. Similarly, finding the highest value out of the EMV values, we know purchase B will be the optimal decision. Compared to the table approach, the decision tree approach actually have one very obvious advantage, is we can go to multiple stages of the problem. If we have to make a decision today and another decision tomorrow and the day after tomorrow, and all these days depend on each other, we can solve the game backward. For example, we try to estimate what will happen in tomorrow, and we solve back to today's, and we get the optimal decision for today's. And that's the advantage of decision tree for solving dynamic multi-stage problems. Thank you.